Albert Einstein. The name itself conjures the image of genius. A wild-haired titan of thought who gifted us the most famous equation in history, E equals mc squared. His theories of relativity are the bedrock of our modern world, from nuclear power to the GPS in your car. For over a century, they have been the ultimate law of the cosmos. But what if that bedrock is starting to show cracks? What if, on the grandest scales of the universe and in the tiniest pockets of reality, the elegant math of Einstein is incomplete? Not wrong, but not the whole story. What if Einstein's greatest equation is beginning to fade? To understand the problem, we first have to appreciate the triumph. In 1915, Einstein unveiled his theory of general relativity. It was revolutionary. He told us that space and time are not a static stage for the universe to play out on. They are a single, dynamic fabric, space-time. Imagine a stretched-out trampoline. That's space-time. Now, place a bowling ball in the center. See how it warps the fabric? That's what massive objects like stars and planets do. And what we feel as gravity is simply other, smaller objects, like marbles, rolling along the curves created by the bigger ones. This wasn't just a neat idea. It made stunning predictions that were proven true, time and time again. It predicted that starlight would bend as it passed the sun, which was confirmed during a 1919 solar eclipse, making Einstein a global celebrity. It explains why Mercury's orbit is slightly off-kilter. And crucially, it's why the GPS on your phone works. The satellites orbiting Earth experience time just a fraction slower than we do down here on the surface. Without correcting for Einstein's relativity, your GPS would be off by several miles every single day. His theory isn't just academic. It's woven into the fabric of our daily lives. For decades, general relativity was the undisputed champion. The first sign that something was amiss came from the stars. In the 1970s, an astronomer named Vera Rubin was studying the way galaxies rotate. Common sense and Einstein's equations told her that stars on the outer edges of a galaxy should move much slower than the stars near the center, just like the outer planets in our solar system orbit slower than the inner ones. But that's not what she found. Rubin discovered that the outer stars were moving just as fast as the inner ones. In fact, they were moving so fast, the gravity from all the visible matter in the galaxy, all the stars, gas, and dust, wasn't nearly strong enough to hold them in orbit. According to the math, these galaxies should be tearing themselves apart. This was a colossal problem. Either Einstein's theory of gravity was wrong on the galactic scale, or there was something else out there. Something massive and completely invisible, providing the extra gravitational glue. Scientists call this mysterious stuff dark matter. It was the first fudge factor, a ghost in the machine, required to make the equations work. We can't see it, touch it, or detect it in any way, yet we need it to be there. We have to assume that 27% of the entire universe is made of this invisible substance. But the universe had an even bigger surprise in store. For most of the 20th century, physicists debated the ultimate fate of the universe. Would it expand forever, or would gravity eventually win, pulling everything back together in a big crunch? Everyone assumed the expansion, which started with the Big Bang, must be slowing down as gravity constantly tugged on everything. Then, in 1998, two separate teams of astronomers pointed their telescopes at distant supernovae. They were trying to measure how much the expansion was slowing. They got the shock of their lives. The expansion wasn't slowing down at all. It was speeding up. Something was actively pushing the entire universe apart, overpowering the pull of gravity on the cosmic scale. This was a direct contradiction of what general relativity predicted. To solve this, physicists had to introduce a second, even more profound fudge factor. They called it dark energy, a mysterious, repulsive force inherent to the fabric of space itself. And the amount we need to make the math work is staggering. It's not a small correction. It turns out that nearly 68% of the entire universe must be made of this dark energy. So let's take a step back. Here is the universe according to our best science today. Everything we can see, everything we've ever observed, all the planets, stars, galaxies, and gas clouds in the entire cosmos, makes up less than 5% of reality. The other 95% is composed of dark matter and dark energy, two mysterious substances we only know exist because Einstein's equations don't work without them. Is this reality? Or are dark matter and dark energy the biggest oops in the history of science, pointing to a fundamental flaw in our understanding of gravity? And there's another, perhaps even deeper, place where Einstein's vision begins to fade, the quantum realm. The 20th century gave us two monumental theories of physics. Einstein's general relativity, which perfectly describes the world of the very large, planets, stars, and galaxies, and quantum mechanics, which perfectly describes the world of the very small, atoms and subatomic particles. Both theories are spectacular in their own domains, but when you try to make them work together, they fall apart. When you try to use general relativity to describe the singularity at the heart of a black hole, a place of immense mass in an infinitely small space, the math breaks, giving you nonsensical answers like infinity. The same happens when you try to describe the moment of the Big Bang. This is the holy grail of modern physics. Finding a theory of everything that can unite the macroscopic world of Einstein with the microscopic world of quantum mechanics. Scientists around the world are working on this, leading to some of the most mind-bending ideas ever conceived. There's string theory, which proposes that at the most fundamental level, everything is made of tiny, vibrating strings of energy. Different vibrations create different particles, like notes on a violin. In this view, gravity is just another type of vibration. Another leading contender is loop quantum gravity. This theory suggests that space-time itself is not smooth and continuous like Einstein believed, but is made of infinitesimally small, discrete chunks, or quanta. If we could zoom in to an impossible degree, we'd see that space and time are pixelated. In this framework, you can't have an infinitely small point, which might solve the black hole singularity problem. These theories are incredibly complex and not yet proven, but they show us that the story is not over. Science isn't about finding an answer and stopping. It's about standing on the shoulders of giants like Einstein to see a little further into the darkness. So, is Einstein's equation fading? In a way, yes, but not in the way a photograph fades to nothing. It's more like a map of your hometown. That map is incredibly useful and accurate for getting around day to day. But if you want to understand the entire planet, you need a different map, a globe. The hometown map isn't wrong. It's just an incomplete part of a much bigger picture. The discovery of dark matter and dark energy and the clash with the quantum world aren't failures of Einstein. They are the new edges of our map. They are the signposts pointing us toward a deeper, richer, and stranger universe than we ever imagined. The quest to go beyond Einstein is the great scientific adventure of our time. It's a story of human curiosity, of challenging our most cherished ideas in the search for truth. Einstein's legacy isn't a final, unbreakable law. It's an invitation to ask the next question. And the answer, whatever it may be, is waiting for us out there, in the dark.